Okay, so we're going to be looking at covalent bonding. First, we're just going to talk about what it is, especially compared to ionic, and then single, double, triple bonds, and then how do we actually draw Lewis dot structures of covalent compounds. So let's start at the beginning. Covalent bonding occurs when pairs of electrons are shared by atoms. So pairs of electrons are shared by atoms. That's big. That's different. In ionic bonding, we had swapped electrons, had a charge, and then they were ionically attracted to each other. Here, instead of a metal and a nonmetal swapping electrons, we have two nonmetals that are sharing electrons in pairs, okay? Since electrons are being shared by atoms, they do not form ions or have charges. There's no pluses and minuses here. Atoms will covalently bond with other atoms in order to gain more stability, which is gained by forming a full electron shell. Okay, what is this actually called? In ionic bonding, when they lost or gained electrons, they were following the Octet Rule, right? So this is the same idea here, Octet Rule. There are some exceptions to the Octet Rule. And if we follow our Lewis dot structure rules, we'll be able to draw them no matter what. But generally for this class, we're going to stay within the Octet Rule group. So by sharing their outermost or valence electrons, atoms can fill up their outer electron shell and gain stability. Nonmetals will readily form covalent bonds with other nonmetals in order to obtain stability, and can form anywhere from 1 to 3 covalent bonds with other nonmetals depending on how many valence electrons they possess. Okay, and that's with one other atom. So one atom can form a single, double, or triple bond with one other atom. And that just depends on how many they need to share. Although it's said that atoms share electrons when they form covalent bonds, they do not usually share them equally. This is important. This is called electronegativity. Okay, so we actually talked about this during the periodic trends unit, electronegativity. Some of them share in their electron hogs more than others. Okay, so now let's look at a single bond. A single bond, single means one, yes? So single bond, we're talking about one pair of electrons. So it's one pair of electrons. How many is in a pair? 2. So a single bond is one pair of electrons, meaning 2 electrons that are being shared between 2 atoms. It is depicted by a single line indicating a single bond between the 2 atoms. Although this form of bond is weaker and has a smaller density than a double and triple bond, it is the most stable because it has a lower level of reactivity, meaning it's less vulnerable in losing electrons. Okay, so what we need to look at is this picture over here, which is hydrogen. Hydrogen is in group 1A. But it is not a metal. It's not part of the alkali metal groups. Hydrogen is a nonmetal. So hydrogen, the way we would normally draw the Lewis dot structure is H and then a dot. Yeah? Okay. Well, if hydrogen needs to follow the Octet Rule, remember, it only has that s orbital. So hydrogen's full electron shell is 2 because the 1s orbital can only hold 2 electrons. So if hydrogen forms a bond with another hydrogen, they're both going to share that pair of electrons. And then they're both happy because they both would have 2 because they're sharing them. And the way that we would depict that is H-H. This is a hydrogen molecule. Okay, you might also see, this is the notation we see the most, but just to show you what it means, that line is a pair of electrons. That's what the line means. So every time you see a line, it's representing a pair of electrons. And they're both atoms of hydrogen is happy because look, this one has 2. And then this one has 2. They're both happy. They're sharing. And hydrogen again is happy with 2. It doesn't need 8 because it only has a 1s orbital. So it's full. Its outermost electron shell is full at 2. Single bond. Okay, double bond. Double, double, double. What does the word double mean? 2, right? Twice as many. So a double bond is when 2 atoms share 2 pairs of electrons. So you have 2 atoms, and between them, they're sharing 2 pairs of electrons. So a total of 4 electrons. It is depicted by 2 horizontal lines between 2 atoms in a molecule. And this type of bond is stronger than a single bond, but it's less stable. Okay? And this has to do with reactivity compared to a single bond. So let's take a look at oxygen. Oxygen over here, okay? We know that oxygen is in group 6A. It's a nonmetal, which means that it has 6 valence electrons. Okay, so that's almost what we're seeing right here. Well, in order to get to 8, in our ionic compounds, didn't it gain 2? So it had a 2- charge. So instead here, it's going to share another 2. So because it needs 2 more, the most that oxygen can bond is 2 bonds. That's the most it can do because it only needs 2 more. Okay? So if we look at the actual oxygen here, you would have 2 pairs of electrons on each oxygen because those ones didn't go away. They're still there. So here's a Lewis dot structure for oxygen. Okay. Here, oxygen is 6. In order to get to 8, it needs 1 more here, and it needs 1 more here. Yeah? That tells us how many bonds it can form. It can only form 2 because it needs 2 more. Another oxygen, if it's going to bond to itself, also needs 2, 1 here and 1 here. All right, well, if we shifted these around and we moved them around, we could have a pair that's here and a pair that's here. Now, if you notice, the other pairs of electrons, they're called lone pairs. They just hang out. They just hang out. There's nothing that they react with. They just belong to oxygen and they stick with oxygen. So that's what we're seeing in this picture, is we're seeing these shared pairs of electrons. In terms of making sure they're all happy, this oxygen has its 2 lone pairs plus the 2 pairs that it's sharing with the other oxygen molecule. Or excuse me, the other oxygen atom in this molecule. And the same thing here. So they're both sharing, and now they're both happy with 8. This oxygen molecule, this is O2. This is the air that you breathe in. So when you breathe in oxygen, you're breathing in O2. Okay, a triple bond, I'm sure you could guess triple. Triple means 3, yeah? So a triple bond is when 3 pairs of electrons are shared between 2 atoms. So triple means you have an atom with an atom, and there are 3 pairs of electrons being shared between them. It's the least stable out of these 3 general types of covalent bonds, and it's very susceptible to electron thieves. Okay? It's also the shortest bond. Okay, so let's look at nitrogen. If I were to draw the Lewis dot structure of nitrogen, I'm going to get a new post-it note. Nitrogen's a nonmetal, and it's in group 5A, so it has 5 valence electrons. Okay? So if I think, how many more does it need to get to 8? So instead of stealing 3 to get to 8 to form a 3- charge, like we had in the ionic bonding, it's going to share 3. It's going to share 3. That means that nitrogen can form a total of 3 bonds. Now that can look different ways. You could have 3 single bonds. It could be like a single, single, single. It could be a double and a single, or it could be a triple. But the max that it can form is 3 bonds because it needs 3. Okay? So if I end up bonding nitrogen to itself, which is what we have in the atmosphere. This nitrogen also needs 3, so we can share a pair here, share a pair, and then this one shares with this one. And that's what we're seeing in this picture here. Now the nitrogens on the top, they still have these lone pairs of electrons. They don't go away. So I'm going to fill those in, because those nitrogen lone pairs, they didn't go away. They're still there. So this nitrogen is N2, and this is what is in the atmosphere. About 70% of the atmosphere, the air, is nitrogen, which is N2, which looks like this. It is a nitrogen atom triple bonded with another nitrogen atom. Okay. There are 7 elements that only occur in nature in pairs if they are not bonded with something else. You need to star, highlight, or circle this because I am expecting you to memorize this. Okay? They are called diatomic molecules. Okay, well, let's think about that word, diatomic. If you were going to split this word up, where would you split it up at? Diatomic. Okay, well, di, the prefix, doesn't that mean 2? Okay. Atom, an atom. And then IC, do you remember what that one means? Pertaining to. Okay, so when we talk about diatomic molecules, we're talking about, or it's pertaining to, 2 atoms in a molecule. The name is the definition. Okay, so diatomic molecules, the 7 elements are hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. Okay, how are you going to remember this? Hofbrinkel, this one right here. You need to star, circle, highlight, something, this. Hofbrinkel. It's all of the symbols. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. Hofbrinkel. I like to pretend that it's like a fairy tale story. Mr. Hofbrinkel and his 7 diatomic elements. Okay, so it's like Snow White, right? The story of Snow White. But here instead, we've got 7 diatomic molecules. So it's Mr. Hofbrinkel and his 7 diatomic molecules. So you do need to memorize this. Hofbrinkel. Say it out loud. Hofbrinkel. There it is. Okay, so Hofbrinkel. Okay, so before we actually talk about the rules for drawing loose dot structures of covalent compounds, I want to do some loose dot structures. Okay, so we already looked at hydrogen, we looked at oxygen, and we looked at nitrogen. In the last unit, I said we're not really going to talk about carbon and silicon yet because they mostly share. Well, now they're going to share. Carbon is in group 4A, which means that it has 4 valence electrons. Okay, so if it needs to get to 8 to share, I need to think about how many times it can share. Well, how many more does it need? It needs 4, right? So because we need 4 more for carbon to get to 8, that means it can share 4 times. 1, 2, 3, 4. That means carbon can form 4 bonds. Now, that can be a combination of bonds. That could be 4 single bonds. That could be 2 double bonds. That could be a triple and a single. That could be a double and 2 singles. Whatever it is, but the most that it can bond is 4 times because it needs 4 more. Okay? Now let's look at, say, chlorine. Chlorine's in group 7A, so it has 7 valence electrons. There's the loose dot structure. In ionic bonding, I said how many more does it need to get to 8? We said 1, so it gained 1 to be a 1 minus charge. Well, here, if I'm sharing, instead of just stealing an electron, chlorine only needs 1 more. That means that chlorine can only bond 1 time because it only needs 1 thing. So it can only bond once. So chlorine will only ever form a single bond because that's all it's got. That's all it's got. It's just 1. So that means your chlorine, your fluorine, F is also in 7A, so that means it can only bond one time. Bromine has 7 valence electrons, needs one more, can only bond one time. And iodine is also in group 7A, which means it only needs one, which means it can only bond one time. So there's a pattern again, okay? So group 7A will only bond once. It will only ever have a single bond because it only needs one. Okay, but let's look at sulfur. Sulfur is in group 6A. Okay, when we talked about ionic bonding, we said that sulfur needs 2 to get to 8, so it would steal 2 and form a 2-. But we're not stealing anymore, we're sharing. But it still needs 2 electrons, right? So that means that sulfur, just like oxygen, because it's in the same group, can share twice. So sulfur can only form 2 bonds because it only needs 2 more electrons to share. So sulfur, that could be a double bond, 1 double bond, or it could be 2 single bonds, but it's only ever going to bond twice. Okay, let's do one more, which is phosphorus. Phosphorus is in group 5A because it has 5 valence electrons. So if I'm thinking how many is it going to need more to get to 8? Doesn't it need 3 more? So that means it can share 3 times. So it can share 3 times, which means the most number of bonds that phosphorus can form is 3. That could be a double and a single. That could be 3 singles. That could be a triple. Right? It could be a combination of things, but it's only ever going to bond 3 times. Okay? Okay. Let's look at our rules here. If you follow these rules, you will get to the correct Lewis dot structure, even for exceptions. Okay? It might look a little funny, but you'll get there as long as you're following your steps. Okay? Like I said, I strongly suggest that we use pencil for the next few days, because if we make a mistake, you can just erase it and then fix it. And the Lewis dot structure is the most important, because if the Lewis dot structure is messed up, then that means your hybridization is wrong, your molecular geometry is wrong, your bond angles are wrong. So we have to make sure we get the Lewis dot structure correct. So covalent compounds and polyatomic ions, which we talked about in the last unit, share electrons to form chemical bonds. To draw the Lewis dot structures for them, a few steps must be followed. So here is the guide. So I'm going to just talk us through it, just read it through, and then we're going to do 2 examples and actually put it into action before we get to the practice. Find the total number of valence electrons for the compound by adding up the number of valence electrons given by each atom. If it is a polyatomic ion, add or remove electrons from the total according to the charge. So just add up how many valence electrons you have total. 2. Write the symbols for the atoms, showing which atoms are attached to which, and connect them with a single bond. Formulas are often written in the order in which the atoms are connected in the molecule or ion. In polyatomic ions, the central atom is usually written first. The central atom is generally less electronegative. Okay, here's how you figure out which one's in the middle. Which one forms the most bonds? Which one forms the most bonds is going to be in the middle. We said up here, chlorine can only form 1 bond. Chlorine is never going to be in the middle. It can only form 1. You need something like carbon, which can form 4 to be in the middle. So whichever atom can form the most bonds goes in the middle. Okay? Number 3, complete the octets around all the atoms bonded to the central atom. So remember, everything else around the center, you put your octets in first. Remember that hydrogen only needs 2. Hydrogen can only bond once because it only has a 1s electron, which can only hold 2 total. 4, place any leftover electron pairs on the central atom. And then this part, even if doing so results in more of an octet of electrons around the atom, that's for exceptions, when we have exceptions to the octet rule. And then number 5, if there are not enough electrons to give the central atom octet, then you try multiple bonds. Don't go in there firing off a bunch of double and triple bonds. Give everything a single bond first, fill in your electrons, and then see what you need to do. Okay? Okay, let's do an example. CF4. Step 1, find the total number of valence electrons. Well, carbon is in group 4A, so it has 4 valence electrons. Plus, there are 4 atoms of fluorine, and each fluorine has 7 valence electrons because it's in group 7A. So, 4 times 7 is 28. 28 plus 4 is how many? 32 electrons. So that means that for our Lewis dot structure, we have to make sure that everyone's happy with an octet because there's no hydrogen here. So everyone's happy with an octet, and we use all 32 electrons. So think, between carbon and fluorine, which one can bond the most? Carbon. Carbon can bond 4 times. Fluorine is in group 7A, which means it needs 1 more, so it can only bond once. So that means your carbon is going to be in the center. Here's a fun fact about carbon. Carbon is the center of attention. Carbon will always be in the middle. Always. Carbon is in the middle. Carbon is like the queen bee. Okay? Carbon is like Beyonce of the periodic table. Do you follow me? It will always be in the center. Okay? Then that means, so that number 2, I'm on number 2. So I put my center atom, which is carbon. And then my fluorines, I'm going to connect them with a single bond all the way around my central atom. So single bond fluorine, single bond fluorine, single bond fluorine, single bond fluorine. You're like, but why did you connect them all to carbon? Well, fluorine can only form 1 bond, right? So you can't attach a fluorine to a fluorine to a fluorine in a line linearly because it can only bond 1 time. So your only option is to stick them all to carbon. Okay, so that's number 2. Take note, each one of these lines, remember, represents 2 electrons. So 2, 4, 6, 8. That's 8 electrons already that I've used. Okay? 3, complete the octets around all the atoms bonded to the central atom. Okay, so if I complete the octets for each fluorine, then each one would have 6 valence electrons around the fluorine. Each fluorine. These are called lone pairs. So each fluorine has what's called 3 lone pairs, meaning it's just an electron pair hanging on to that atom. That was step 3. Okay, now let's count how many electrons have we given homes to. We have 32 total, okay? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, I've used all my electrons. I can't put any more dots or lines here. Now let's check your octets, okay? So check your octets. Fluorine has 8. This top fluorine has 8 because it's sharing a pair with carbon. This fluorine has 8 because it's sharing a pair with carbon. Same thing for this fluorine on the bottom and the one on the left. Now check carbon. Does carbon also have 8? Yeah, because it's sharing 4 times. So everybody has a complete octet. We're done. Smiley face, check mark, ding. You got it right. This is a Lewis dot structure of CF4, which is carbon tetrafluoride. Okay, let's do another example. HCN. Okay, so step one is going to be counting up your total number of valence electrons. Okay, so hydrogen is in group 1A, so it has 1 valence electron, plus carbon is in group 4A, so it has 4 valence electrons. And nitrogen is in group 5A, so it has 5 valence electrons. So 1 plus 4 plus 5 equals how many? 10 electrons. So that means we have 10 electrons that have homes, okay, that need homes. So step 2, write the symbols for the atoms and connect them with a single bond. Who is the center of attention? Carbon. So who is in the middle? Carbon. Okay, so carbon is in the middle. Remember how we said that sometimes they're written in how you draw them? HCN. So the C is in the middle. So that means I'm going to single bond to a hydrogen and single bond to a nitrogen. Okay, so right now I've used 4 electrons. Let's talk about who's happy. Is nitrogen happy? Yes. It only has 2 electrons right now, so it's not happy. It only has 2. Carbon only has 4, so it's not happy. But hydrogen is sharing 2, so hydrogen's done. Hydrogen only needs 2. So we're done with hydrogen. Step 3, complete the octets around the atoms bonded to the central atom. Hydrogen doesn't need any more because it already has 2, so it's done. So I'm going to add the extra electrons to nitrogen. Okay, so nitrogen, if I add them here, 2, 4, 6, 8, 10, that would be all of my electrons. Okay, so now let's check. Hydrogen's still good with 2. Nitrogen is now good because it has 8, but is carbon happy? No. Okay, so this is when you start using multiple bonds because carbon is not happy and there's no more electrons to give. I've already used all 10 of them. So now we start taking electrons from the outermost and start putting them in a double, single, or a double or triple bond. So I'm going to take 1 pair of electrons from nitrogen and I'm going to make another bond. I just made a double bond between this carbon and this nitrogen. Okay? Do you see why I said pencil, pencil, pencil? So now let's double check. Hydrogen is still good. Nitrogen is still good. Still has 8. 2, 4, 6, 8. And carbon now has 6, so we're making progress, but carbon's still not happy. So what are we going to do? Just take another pair of electrons and put it in a bond. So I'm going to take this next pair of electrons. Come on. There we go. I'm going to take this next pair of electrons and make another bond. So now I have a triple bond. So now let's double check. Hydrogen's still good with 2. Nitrogen has a triple bond, so that's 6 electrons, plus 2 is 8. And carbon now has 8. A triple bond, which is 6, plus 2 from a single is 8. Yay, happy check mark ding. Our structure is done. So the first thing you need to do is add up how many total valence electrons you have to work with. You can't just be adding electrons left and right. They have to come from somewhere. 2, think about who is going to bond the most, and that goes in the middle. Remember, carbon is the queen bee, okay? And then add your octets to the outside atoms, and if you need to start doing double or triple bonds, add them in. But you got to make sure that you are following your octets, okay?